Hello everyone and welcome back to another Calculus 2 video. In this video, we are going to look at the calculus behind parametric curves. So we're going to start by looking at how do we take the derivative of something that's written parametrically. So if we look at the function x equals, and it's some function written in terms of t, usually that t represents the parameter time, and then y equals y of t. If we want to find the derivative, we could take the derivative of x with respect to t, and we're going to take the derivative of y with respect to t. So to find dy over dx, remember this is the derivative of y with respect to x. We don't need to solve this necessarily as y equals a function in terms of x. We could take the derivative of y with respect to t and then divide that by the derivative of x with respect to t. If you think about how fractions work, if we do keep, change, flip on this, we will get dx over dt. So let's look at a few examples. In example 1a, we have the function x of t equals t squared minus 3, and y of t equals 2t minus 1, and t is bounded between -3 and 4, and they're asking us to calculate the derivative. So to find the derivative of x with respect to t, we're just going to take the derivative the same way we normally do, and that derivative is just going to be 2t. The derivative of y with respect to t would just be 2. So if I want the derivative of y with respect to x, I could take the derivative of y with respect to t, and then I'm going to take the derivative of x with respect to t, and then I'm going to divide those. So I'm going to have 2 over 2t, which is going to be equal to 1 over t. So notice this derivative is undefined when t is equal to 0. So let's analyze that a little bit more. What's happening when t is equal to 0? So I'm going to graph this function, and I'm going to cheat a little bit, and I'm going to graph this in Desmos. So to graph parametric equations in Desmos, I'm going to use parentheses. My x-coordinate is defined by t squared minus 3. And then my y-coordinate is defined by 2t minus 1. And I'm looking at what's happening between -3 and 4 for t. So there's my parameters. So here's my graph. And we would have gotten the same thing if we created that t-table like we did in the last section. You can see it's like sideways quadratic. So when t equals 0, we're looking at the point -3, -1. And if we look at the point -3, -1, we see that's where we would have a vertical tangent. So it makes sense that that derivative would be undefined at that location. So let's look at B. We're looking at the function x of t equals 2t plus 1, y of t is equal to t cubed minus 3t plus 4. This function is defined for t between -2 and 5 inclusively. So if I take the derivative of x with respect to t, I'm just going to get 2. If I take the derivative of y with respect to t, I'm going to get 3t squared minus 3. So dy over dx equals dy over dt over dx over dt. So dy over dt is 3t squared minus 3. dx over dt is 2. And I could write that as 3/2 t squared minus 3 over 2. So let's see if we can find critical points. To find critical points, remember we take the derivative and we set it equal to 0. So 3t squared, 3/2 t squared minus 3/2 is going to be equal to 0. If I move that 3/2 over, and then I divide by 3/2, I'm going to get t squared is equal to 1, which means that's happening at plus and minus 1. So let's see if we can figure out what's going on there. So when I plug in 1, my x-coordinate would be 2 plus 1, which is 3. And my y-coordinate would be 1 minus 3 plus 4. which is 2. So we're looking at the point 3, 2. And then when I plug in -1, x of -1 would be -2 plus 1, which is -1. And y of -1, so that's going to be a -1 cubed, which is -1. -3 times -1 is now a +3, and then we're going to have +4, which is going to be 6. So we're looking at the point -1 and 6. So let's look at what's happening on the graph for these functions. So I'm going to go back to Desmos and graph this. So if I graph this function, here's my graph. It's a cubic function. And I can find that in rectangular by solving this equation, the x equation for t, and then I would have a substitution for t and y. So we can see that cubic, what it is. It is restricted between t equals -2 and 5. So we can see our graph extends pretty far up on that in that first quadrant. When we set that derivative equal to 0, we found 2 interesting points. Those are the critical points, and that's happening at -1, 6 and at 3, 2. And we can see that we have a maximum at -1, 6 and a minimum at 3, 2. So now let's look at C. And I'm going to recopy the problem down here. So we have x of t is equal to 5 cosine of t. Y of t is equal to 5 sine of t. And this works for 0 is less than or equal to t is less than or equal to 2 pi. So the derivative of x with respect to t, the derivative of cosine is negative sine. So it's going to be -5 sine of t. And then the derivative of y, the derivative of sine is cosine. So this is going to be 5 cosine of t. So dy over dx is dy over dt over dx over dt. So we're going to have 5 cosine of t over -5 sine of t. So there's our derivative, negative cosine over sine. Or we could write this as negative cotangent t. We want to know where this is equal to 0. So that's going to be equal to 0 wherever negative cosine of t is equal to 0, or where cosine of t is equal to 0. On the interval from 0 to 2 pi, cosine is 0 at 2 places on that interval, and that's pi over 2 and 3 pi over 2. So let's plug in pi over 2 and 3 pi over 2. So if I plug in pi over 2 to find the x-coordinate, I'm going to have 5 cosine of pi over 2, which is going to be 0. And then the y-coordinate at pi over 2, we're going to evaluate 5 sine of pi over 2, which is going to be 5 times 1, which is 5. So we're looking at the point here, 0, 5. And then if I plug in 3 pi over 2, x of 3 pi over 2 means we're going to evaluate 5 cosine of 3 pi over 2. And that's going to be 0. And then if we plug 3 pi over 2 in for y, or the y equation, in for t, we're going to have 5 sine of 3 pi over 2. And that's going to be 5 times the -1, which is a -5. So we're looking at the point 0, -5. So remember, this guy's going to graph a circle. We're going to see that in Desmos. And then we'll see a max and a min here. The maximum is going to happen at 0, 5. Notice that's the bigger number. and the minimum is going to happen at 0, -5, with that y coordinate being the smaller number. Cosine of t, sine of t, from 0 to 2 pi. Here's our circle. We're graphing the point 0, 5, which is our max, and 0, -5, which is our min. You can see those come out on that graph as well. Let's look at finding the equation of a tangent line defined by a set of curves parametrically. So to find the equation of a tangent line, you got to have two things. You got to have a slope, and then you have to have a y-intercept. And if you don't have a y-intercept, you need a point that's on the graph. Okay. So our goal is to get it into y equals mx plus b form. We can use point slope equation, y minus y1 equals m times x minus x1. So we'll start by finding the slope. To find the slope, we're going to take the derivative, and we're going to plug in t equals 2 for that. So x is equal to t squared minus 3, so that means x prime. The derivative of x with respect to time is 2t. Y of t is equal to 2t minus 1. So the derivative of that with respect to t is 2. So dy over dx is dy over dt over dx over dt. So we're going to have 2 over 2t, which is 1 over t. We want to know what's happening at that moment when t is equal to 2, so we're going to plug a 2 in, and we're going to get a 1/2 for our slope. So now let's find our point. We're looking at what happens at t is equal to 2, so I'm just going to use that. When I plug in 2 in for my x, I'm going to have 2 squared minus 3, which gives me an x coordinate of 4 minus 3, which is 1. And then when I plug 2 in for my y, I'm going to have 2 times 2 minus 1, which is going to give me a y coordinate of 3. So I'm looking at the point 1, 3. So I have a slope. I have a point on the graph. So I'm going to use point slope formula. Y minus y1 equals m times x minus x1. So we're going to have y minus 3 equals 1/2 times x minus 1. So y equals 1/2 x minus 1/2. Now I'm going to add that 3 over. So y equals 1/2 x plus 5/2. So there's our slope of the tangent line. So now let's talk about second order derivatives. How do we take a second derivative of something that's written parametrically? Well, we know the second derivative is the derivative of the first derivative, so let's apply that idea. So if I take d over dx of dy over dx, so I'm going to do some fancy math off to the side, and I'm going to work with this here. So we've got d squared y over dx squared. That's a notation for the second derivative, and we know what that means is we're taking the derivative of the first derivative. So I'm taking d over dx of dy over dx, and we found dy over dx by finding dx over dt, dy over dt divided by dx over dt. So I'm going to write that in. So d over dx, and we're going to find dy over dx by looking at dy over dt over dx over dt. So if we had 3 times some kind of fraction, what that means is we would take that 3 and think about it as 3 over 1. So we would multiply 3 by 1/2 times 1 times 1/3. The same thing is going to happen here. I'm thinking about d over dx times that top dy over dt And I could think about that d over dx being divided by 1, and then I would have 1 times dx over dt. And then I know if I have fractions, let's say I have a over b times c over d, I could rearrange those. That's really ac over bd. And I could think about that as a over d times c over b. I could change the order because multiplication is commutative under the real numbers. So I'm going to think about that here. I can change the order of what's going on with these symbols. So I could think about d over dt times dy over dx, and all that's over dx over dt. And that's where our derivative equation is coming from for that second derivative. I'm going to take, that's supposed to be an x, dy over dx. So it's d over dt times dy over dx divided by dx over dt. It's just a manipulation of the variables there. So what that means is I'm going to take my first derivative, and I'm going to take that derivative with respect to time, and I'm going to divide that by whatever the derivative of x was with respect to t. Notice this is a first derivative of x, not a second derivative. So you have to be very careful with taking that derivative. So we want to find in example 3 the second derivative for the curve x of t equals t squared minus 3, y of t equals 2t minus 1. So we're going to find x prime, which is 2t, and then we're going to find y prime, which is 2. So dy over dx is dy over dt over dx over dt. dy over dt is 2, dx over dt is 2t. So that reduces to 1 over t, or we can think about that as t to the negative 1. So if we want to find the second derivative, d squared y over dx squared, it's going to be the derivative with respect to t of dy over dx divided by dx over dt. So I'm going to take the derivative with respect to t of t to the negative 1, and now I'm going to divide that by dx over dt, which was 2t. Notice I did not take a second derivative there. It's the first derivative of x with respect to time. So let's simplify this. The derivative of t to the negative 1 is negative t to the negative 2, and we're dividing it by 2t. So this is negative 1 over t squared divided by 2t. And if I do keep change flip, I'm going to have negative 1 over 2t to the third. So that's my second derivative. d squared y over dx squared. And notice that all the derivatives we've taken of parametric equations are written in terms of time, and that's pretty common for derivatives.